This is our third recorded lecture that's supposed to be on the last Monday, 23rd March. Today we'll continue discussing the rest of the topic of chapter 4, the continuous random variables and their properties, and we'll start with the cumulative distribution function. Cumulative distribution function, I'm sorry, here this is cumulative distribution function, not density. Cumulative distribution function, I will fax this and then I'll upload them on Moodle. For a continuous random variable y that have a BDF is defined by small f of y, the cumulative distribution function, or sometimes we call it distribution function of a random variable y, and denoted by f capital of y, is given by this formula. If we try to remember the same definition for the discrete random variable, the cumulative distribution function, and we here denote it by f capital of y, f capital of y of a certain value y, in fact it gives the cumulative probability, or the probability that the random variable y, and here we write y as a capital letter, less than or equal a certain value, and we denote it by small y. So if we find y here on this real line, and if we imagine that we have the BDF, which we denote it by small f of y, is defined by this curve, and we need to find the probability that the variable y take less than or equal a certain value y. So all what we need is to compute this shaded area on the left under the CDF, on the left of the value small y. So what we need is to compute this shaded area. So this means if we define the range over which y take value, this will be from negative infinity to infinity. So this means we need to find this area under this curve, which is here denoted by the shaded area, according to as a probability statement. This means we need to find that probability that y take value greater than negative infinity and less than a certain value y. So this will be a finite integral over the BDF over the specified interval, which is from negative infinity to y. By this way, we'll define how to compute a probability statement using the BDF. So at the end, the f capital of y is defined by the integral of the negative infinity to certain value y for the BDF. That's why we are finding the probability that y take value up to a certain value small y. Let's now try to read the definition. Here f capital of y is equal to probability that y less than or equal a certain value of y is computed by this integral. This gives the area under the BDF curve up to a value y equal a certain value y, small y. Okay, so here we in fact in the graph on the left here we assign the certain value y as y naught. So f capital of y naught is computed as the integral from negative infinity to y naught over the BDF. Sometimes we can we write this BDF in terms of t, and then we integrate with respect to t to avoid confusion between resubstituting with y if it is written in y in terms of y. Fine. Graphically, this represented by, which is the same as I represent on the board, and the graph here on the right, in fact, it tried to find the relation. this graph here, try to link the relation between the BDF. I think this graph is the BDF. This needs to be fixed. This is the BDF. I'm here representing is the random variable as x not y. So this is the BDF of a variable, say x, and this is the cumulative. This is the CDF, and this is the BDF. And we imagine a value, the certain value here equal 8. I'm trying now to read the point on the function, on the curve here, on the BDF and on the CDF. On the BDF, these values in fact give us the height. The height of this value will be here, will be small f of 8. This is a small f of 8. This is a height from this point to the curve. This is the height. Fine? But the area under the curve from the lowest value of y up to 8, which is given here by this shaded area in gray, in fact this gives us the probability that x less than or equal 8, which is f capital of 8. Right? So if we represent the CDF by this graph and we try to read the value from the point 8 on the intersection over this point intersected on the f capital, which is f capital of 8, so this value here represent this area. This is the link I mean. So this shaded area represented by a value on the f capital of x axis here, a BDF and associated CDF. So this is the link between these two functions. Okay. Now move to still we are again, this is cumulative distribution of the density function. This is cumulative distribution function. Definition: a random variable y with distribution function f capital of y is said to be continuous if f capital of y is continuous for any value of y between negative infinity to infinity. So the variable is continuous if f capital of y is continuous. Okay, continuous such as this form takes it from 0 up to, if we read this value, we'll find it equal to 1, and we'll then explain why this is equal to 1. Again, a continuous random variable could be defined based on its cumulative distribution function. That means if we have a random variable y and we have its associated f capital of y, so this f capital is completely represent the distribution of y because this function is unique. This function is unique, so we call it a uniqueness property of the CDF. Now move to discuss the properties of the cumulative distribution function. In fact, we have some properties. The first one, if we have two different points y1 and y2, such as y1 is less than or equal y2. The first property tells us that the f capital of y, which is the cumulative distribution function, is non-decreasing function. So if we have two values on the y-axis, which is y1 and y2, and again I emphasize that y1 and y2 are both certain value on the range or the domain of the variable y. Okay, then the CDF, the value of the CDF at y1 will be less than or equal the value of the CDF at y2. So this is represented by this figure. If we have y1 here and y2 here, and we know that y1 is less than or equal y2, then this is the graph, the curve of the cumulative distribution function. As we see, it is increasing or constant. It never be decrease. Fine. So if we try to find the value, the F capital at y1, this can be done by moving upward and then find this intersected value on the Fy axis to read this value. So this is the F capital of y1. Again, for y2, to find F capital of y2, and we'll find if y1 is less than or equal y2, then F capital of y1 less than or equal F capital of y2, which is tell us the first property of the cumulative distribution function, a non-decreasing property. Okay, it may be more clear if we define, if we have another function, a decreasing, say another function, say g of y. In the decreasing function, I just wanted to show you. Let's do it there in the board. If you imagine we have another function, say g of y, and this function is decreasing. It's g of y, any function, any other function, and these are the random variable, and we have y1 and y2 such that y1 is less than or equal y2. What this will be reflected by the function g. If we try to find the value of the function at this certain point, we'll read this as g of y1. If we try to read this function, if we try to read this value on the function, this will give us the value of the function at y2. So here we have y1 is less than or equal y2, but this implies that g of y1 is greater than or equal g of y2. So here what happened for the inequality? It reversed. It's reversed to the other direction. So this is occurred because gy here is what? It is a decreasing. It is decreasing. So y1 for the decreasing function less than or equal y2. This imply to g of y2, g of y1 greater than or equal g of y2. This happens when g is a decreasing function, which is not the case for the cumulative distribution function. This was the first property of the cumulative distribution function. Now next to the second property. In the second property, we say that the f capital of y, the cumulative distribution function, in fact, it lies between 0 and 1. So the lowest value of this function is 0, and the upper value of this function is 1. So we can say that f capital of y represent somehow a value of a probability, because the probability always positive and lies between 0 and 1. This happened because the f at the lower limit of y equal to 0, which is limit of the CDF when y tends to negative infinity. And when we substitute for y with its upper limit, this will give us the limit of f capital of y at y tends to infinity, which is give us to 1. If we try to explain this property more, okay, we know that y is a random variable that have a BGFY, where y is defined between say for example A and B. يعني I will يعني say A and B are two certain constant that belongs to the real value set of the real values. Fine. So the BDF is only defined on on support. This is our BDF. It's only defined on the out of this support, the value of the CGF equal to 0. So we say that f of y equal to a certain value here, while y between a and b, and 0 otherwise. Fine. Okay. Now if we move to find when y is less than or equal a. When y is less than or equal a. Fine. And need to find f capital of y. This means probability that y less than or equal a certain value called y. Fine. And here we have y is between negative infinity and a. So this will be computed as finite integral from negative infinity to a to the BDF. Fine. This in fact will be, here we are substituting on the interval, by definition, this probability that y less than or equal certain value y, this will be y. Here if we have y less than or equal a, what is the value? This is what we know. Here we know that y is less than or equal a. What is the value of the BDF? In fact, when y less than or equal a, the value of the BDF equal to 0. So within this interval or within this support, the BDF is not defined. So this will be negative, that is integration from negative infinity to y to 0 function dy, which is 0. Okay, then the limit of f capital of y when y tends to its lower limit equal to f capital of a equal to 0. This is in fact the property that we are discussing here. Okay. Now let's move to the other part, or the other equation in the property. Okay, the other equation in the property. Let's move this area. Now let's imagine that y takes the value greater than or equal b. Fine. And need to find f capital of y within this range. This means probability that y less than or equal y, which means integration from negative infinity to y, and y takes the value up to a. Here y takes the value from negative infinity, which is a, negative infinity to a, right? This part from negative infinity to y, and y here greater than or equal b, So from negative infinity to y will be partitioned into from negative infinity to a, from negative infinity to a for the BDF, which here from negative infinity to a equal to 0. Plus from a to b for the BDF, plus from b to y through the BGF. Here the BGF above B is not defined, it's equal to 0. So here again, this is 0. So this CGF, when y limits tends to B, will be at the end is the integration over the BDF over its whole support from A to B, which is 1. I hope this point is clear. I hope this point is clear. That's why we say that limit of the f capital of y when y tends to its lower limit, which is here A, equal to f of A equal to 0. And the limit of the CGF when y tends to upper limit, which is here B, which is f of B, have to be 1. Again, why it should be 1? Because here, in fact, this is probability that y less than or equal B. This means the probability that y between A and B, which is the integration over the whole support of the probability density function, which is 1. Fine? While here probability, we are finding a probability that y less than or equal A. We are integrating to find this probability. We are integrating over 0 because the BGF is not defined. So this equal to 0. I wish this is clear and understood. That's why here in this graph we say when y tends to infinity, the f capital of y approach to 1, while when y tends to negative infinity, f capital of y approach 0. Fine. Now move to the next property. If y is a continuous random variable and b are real constant, a and b are real constants, with a less than or equal b, then this probability can be, in fact, be computed using the CGF. It's in fact equal to the CGF at the higher value minus the CGF at the lower value or the lower bound. This is the upper endpoint and this is the lower endpoint. So this property in fact show or tell us that how probability can be easily computed from the CGF. Let me show how this is why this probability can be expressed by this way in terms of the CGF. Now move to our board to explain this more. Here we need to find the probability that y tends between two endpoints A and B, and A and B are real values. Okay, let's try to I'm imagining or assuming that we have a random variable that is defined from negative infinity to infinity like this, and we are specifying a certain interval which is A to B, and we need to find this area under the BGF. So one of two methods can be applied here to find this probability as the area under the BGF, which can be found by the integral over the BGF over this interval. So this is one method. The other method, which is this can be also done by subtracting this area from negative infinity to A from the area from negative infinity to B. So if we imagine this area is shaded in red, this represents probability that y less than or equal A. Probability is that y less than or equal A. And if we represent also this area that y less than or equal b. So the shaded area in purple here can be computed by subtraction. Subtract this area, or subtract this area, let's say it 1, from this area, let's say 2. So this will be the area 2 minus the area 1. Area 2 is probability that y less than or equal b, minus the area 1, which is probability that y less than or equal a. So if we subtract this area from this area, it will give us the probability that y lies between a and b. What we call this probability is in fact the CGF at y equal b, and this is the CGF at y equal a. So that's why the probability in this statement can be transformed into a statement with respect to the cumulative distribution function, and why that show us how can we easily compute the probability from the cumulative distribution function. And now move to property number 4, which is at the point where fy, the BGF, is continuous, we can find the probability density function from the cumulative distribution function by differentiation. We know that we can find the cumulative distribution function from the BGF by integration, so we can find fy, the BGF, from the cumulative distribution function by the reverse operation, which is differentiation, but this can never be done unless the BGF is continuous. The fourth property shows how the BGF can be easily derived from the CDF by differentiation. Now move to solving some exercises over the cumulative distribution function. Move to exercise number 1. We have a certain BGF of this form, and we need first to find the cumulative distribution function of this BGF. Here is the exercise now. To find the cumulative distribution function according to the definition, this will be f capital of y equal to the probability that y less than or equal small y. This would be the integral from negative infinity to a certain value y for the BGF, and we'll write it in terms of t. This is the theoretical definition. Move to our exercise. All what we need here is to substitute for the lower limit with 0, and here we still have y in the upper limit, and then we'll substitute with the BGF in terms of t, which is 3t to the power 2 dt, which is equal to 3 divided the new power t to the power 3 from 0 to y. So this will be y to the power 3. So the first step is to find the distribution function when y between 0 and 1, which is a change or a change within its within the support of the BGF. The next step is to try to find the limit of the fy that we just compute when y tends to lower limit, which is here equal to 0. So this means f of 0. F of 0 is 0 all to the power 3, which is 0. So the condition here is satisfying. And number 3 is to find the limit when y tends to its upper limit, which is here 1, f of 1, which is 1 to the power 3, which is 1. So at the end, we write f capital of y in the complete form that start from 0 and end up to 1, and here 0 when y less than or equal 0, and 1 when y greater than or equal 1. When y greater than or equal 1. And while y between 0 and 1, while y between 0 and 1, the f capital phi equal y to the power 3. Now we need to find this probability that y between half and 1 using both the BDF and the CDF. Let's now do this. Using the CDF, probability that y takes the value the probability that y takes the value from half to 1 equal to f capital at y equal 1 minus f capital at y equal half. And here we have 0.5 to 1 lie in this range, so we'll substitute in each time in the form of y to the power 3. So this will be 1 to the power 3 minus half to the power 3, which is 1 minus 1/8, which is equal to 7/8. We need to find this probability using the BDF. This will be computed as follows. Probability that y takes the value from half to 1 using the BDF. This means we need to find the area over this interval from the BDF, or the area under the BDF over this interval, which can be found or computed as the finite integral over this interval to the BDF. Which is 3y to the power 2 dy from half to 1, which is 3 divided 3y to the power 3 from half to 1, which is equal to 1 minus half to the power 3, which is 1 minus 1/8, which is again 7/8. We still need here, in first one, we need to graph both the BDF and the CDF, and I don't want you to be worried about graphing. The graphing will not be a task that I may ask you to do. So if we here find the final answer, this will be the graph here of the BDF and here for the CDF for such distribution. Now move to the next exercise or the next example. We have the length of a time required by a student to complete a 1-hour exam is a random variable with a density function given by this form. This form represents a BDF, and we need to find the value C. To find the value C, such that this is a BDF, here we have y is between 0 and 1. So this means the integral all over the support of the BDF equal to 1. Substituting for the support by 0 to 1, and the BDF with this formula above, so C y to the power 2 plus y dy, all this equation have to be 1. Finding the integral, this will be C over 2 y to the power 3 plus y to the power 2 divided 2, and this will be substituted by the limits of the integral from 0 to 1. Then C divided 3 times 1 plus 1 divided 2, which is half minus 0 equal 1. Then C divided 3 equal 1 minus half, then C divided 3 equal half, then C equal 3 divided 2. And don't forget to rewrite the PDF after writing down the value of C. Then the PDF will be f of y equal to 3 over 2 y to the power 2 plus y, and y takes the value from 0 to 1. And now move to the next question. We need to find the cumulative distribution function. The cumulative distribution function to be computed, this means within the support of y, we find f capital of y as the integral from the lower limit up to a certain value y for the PDF intermediate of t, which equal to the integral from 0, which is the lower limit in this case, to the value of y for 3 over 2 t to the power t square plus t dt. I will move writing here in this site. So the f capital of y will be 3 times 2 by 3 t to the power 3 plus t to the power 2 divided 2, and then substitute from 0 to y. Will be 3 here will be eliminated with 3. Then we have y to the power 3 divided 2 plus y to the power 2 divided 2 minus 0. And at the end, we need to find the f at the lower limit, which is 0 to the power 3 divided 2 plus 0 to the power 2 divided 2, which is 0. And the limit at the upper limit, which is 1. So this will be 1 to the power 3 divided 2 plus 1 to the power 2 divided 2, which is half plus half, which is 1. We still need to write the cumulative distribution function in its final form, and it's very important to write the form of the cumulative distribution function that starts from 0 when y tends to its lower limit, and equal 1 when y tends to its upper limit, and it takes a value of half times y to the power 3 plus y to the power 2 when y takes the value between those two limits. So this is very important to write the cumulative distribution function in its final form, and then move to the next question. The next question we need to graph. I think I will skip the graphing. I will show you the graph on the slides. Next, use the cumulative distribution function part 2 to find f at -1 and 0 and 1. When f at -1. Here we know that -1 belongs to y less than or equal 0. So f at -1 equal to 0. F at 0 equal to 0, and f at 1, which is 1. So all what we need is to find the form of the cumulative distribution function that we need to substitute in with the value indicated between brackets. So if we need to find f capital of -1, we'll try to search in this different support of y, or this domain of y, which of them -1 belong. So -1 belongs to this interval. So the value of f at y equal to or approach -1 is 0. What about f capital of 0? F capital of 0 is defined in this inequality here, in this direction. So f capital of 0 equal to 0 as well. F capital of 1 is here because y 1 is included in this interval, so f capital of 1 equal 1. So all what we need now is to answer number 5. Find the probability that a randomly selected student will finish in less than half an hour. We know that we are saying that the student completing the exam within 1 hour. So y, which is between 0 and 1, indicate to the time. So 1 for 1 hour and 0 for non-value. If we need to find that the students need, or the probability that he finished the exam in less than half an hour, so this means to find the probability that y less than or equal half is less than half an hour. So all what we need now is to find the probability that y less than or equal half, which is f capital at y equal half. So all what we need is to substitute in the formula of the cumulative distribution function with half. So to find this probability, this means we need to find the probability, that y less than or equal half equal f capital at y equal half. So this can be given by direct substitution in this form, which is half 1/8 plus 1/4, which is, I think, here 8, 3 times 2, so this is 3 divided 16. Yes, 3 divided 16, this is actually the value. Okay, number 6, given the particular student needs at least 15 minutes to complete the exam, find the probability that she will require at least 30 minutes to finish. We know that at least means greater than. So if we have a particular information that the student already needs at least 15 minutes to complete the exam, what is the probability that she will require at least 30 minutes to finish the exam? As you can see here, this is a kind of conditional probability. So this be computed by the probability that y greater than 0.5, which means half, half, given y is greater than 0.15, which is 15 minutes. I think 15 minutes, it means 0. Which is quarter. Point 24. Okay, this means, by definition of a conditional probability, this means the probability that y greater than 0.5 and at the same time y is greater than 0.25 divided by the probability that y give greater than 0.25. Okay, if we have here two different intervals, if we substitute here for y greater than quarter and y greater than half, greater than quarter represented by this area, greater than half will be represented by this area. Let's make it with a different color. This is greater than half, so this is means the intersection between those two intervals implies to probability that y greater than half divided probability that y greater than 1/4. So this is 1 minus f of 0.5 divided by y minus f of 0.25. All what we need is to substitute in the cumulative distribution function in both formulas. Don't forget we have 1 minus. We have here 1 minus. Let's remove this to save space. So this equal to 1 negative half, 1 negative half, and here 1/8 plus 1/4 1/4. Similarly here this is 1/4, which is 1 divided 16 times 4 minus 1 divided 16. At the end I have the answer of this question. This is given here as yes, 104 divided by 123. I think up to this point we finish cumulative distribution function. Let's continue in the next time discussing the expectation and variance moment and moment genetic function. Assalamu alaikum.